A group G is cyclic if G equals powers of some element in G. There's some element A of G such that the cyclic subgroup generated by that element is all of G. Say that again. We know this set, that's the set we did the first proof with today. That's the cyclic subgroup generated by A. It is a subgroup of G. If it equals all of G, if every element of G is a power of A for some A, then G is a cyclic group. Our prototypical examples of cyclic groups are Z and Zn. Are there other cyclic groups? Yes, there are. Although, with respect to classifying groups, these prototypes are it. Meaning any other cyclic group is going to be isomorphic to one of these. And by the way, n is an arbitrary positive integer here. So there's different cyclic groups of different orders. There's Z1, Z2, Z3, Z4, Z5, etc. But only one Z. But remember, it's a little tricky here. The operation is addition in these, not multiplication. So instead of powers of elements generating the group, you have to think about adding elements to generate the group. In Z, what's a generator? What's an A? Such that all summations you can make of that element or its inverse give you all of Z. Not zero. The cyclic subgroup generated by zero is itself. When you add zero to itself any number of times, you still get zero. 1 is a generator. 1, first of all, equals itself. 1 plus 1 is 2. 1 plus 1 plus 1 is 3. 1 plus 1 plus 1 plus 1. Did I say 4 ones? Is 4. 1 plus 1 plus 1 plus 1 plus 1 is 5. 1 plus 1 plus 1 plus 1 plus 1 plus 1 is 6, etc. Also, -1, the additive inverse of 1, is in the cyclic subgroup generated by 1, because that's like raising to the -1 power. Raising to the 0 power, so to speak, or not really raising to the 0 power, is 0. In an additive group, we're not really raising to powers, and so don't let that confuse you. 0 times 1 is 0. -1 is in there. -1 plus -1 is -2 is in there. -1 plus -1 plus -1. Did I say 3 of them? Is -3 is in there, etc. Yeah, 1 is a generator, as is -1. And no other number is a generator. 2 is not a generator. What are all the things you can get by adding 2 to itself? All even numbers, both positive and negative, when you include adding its inverse, -2. And 0, by definition, effectively. 3 is not a generator. 4 is not a generator. -2 is not a generator. -3. 1 and -1 are the only generators. Of this infinite cyclic group. By generator, I mean an A that in the abstract has powers equal to the group. Although in this case, it's really multiples of these things equaling the group. You might wonder, does Z have any cyclic subgroups that don't equal itself? Say that again. You might wonder, does the integers Z have any cyclic subgroups of it that don't equal it? Yeah, it actually has infinitely many cyclic subgroups that don't equal it. Well, there's the trivial one. 0 generates just itself. It's the trivial subgroup, but you could say it's cyclic. 2 and -2, yeah, they do generate all even integers. And it is a cyclic subgroup, not equal to the entire group. 3 and -3 generate all multiples of 3. and it is a subgroup, a cyclic subgroup, not equal to the entire group, etc. I could keep going. This group Z, the integers, has infinitely many cyclic subgroups that don't equal it. And in fact, they're all going to be isomorphic to Z, amazingly, even though they don't equal Z, except for the trivial one. I haven't said what isomorphism means. I mean, I hinted at it with finite groups that the Cayley tables can be made to have the same form if you put the elements in the right orders, at least. What does isomorphism mean with infinite groups? I haven't said yet. But even though these things here, starting with this one, are cyclic subgroups of Z that are proper, they don't equal Z. They're distinct. They turn out to be isomorphic to Z as groups. Algebraically, they behave the same, you might say. Zn, of course, as a set is 0, 1, 2 through n minus 1. And it's understood, again, that it's addition mod n. Whenever you write Z by itself, it's understood in group theory that that's ordinary integer addition. Whenever you write Zn, it's understood that you're doing addition mod n. What's the generator of Zn? Well, one is. It turns out the inverse of 1 is as well. What's the inverse of 1 in Zn? It's n minus 1. Are these the only generators? Answer is, it depends. Sometimes yes, sometimes no. It depends on what n is. All right. May or may not be the only generators. It depends on the value of n. To give you a couple examples, Z5, for example, actually has 4 generators. 1 and 4 are certainly generators, 4 being 5 minus 1. But every non-zero element is actually a generator. Why? Because you think about these sets in terms of adding these elements to themselves. 1 plus 1 is 2, 1 plus 1 plus 1 is 3, 1 plus 1 plus 1 plus 1 is 4, 1 plus 1 plus 1 plus 1 plus 1 is 0, mod 5. Here, think about adding 2 to itself. 2 plus 2 is 4, 2 plus 2 plus 2 is 6, mod 5 is 1. That's 2 plus 2 plus 2. 2 plus 2 plus 2 plus 2 is 3. 2 plus 2 plus 2 plus 2 plus 2 is 0. And I could do similar kinds of things with these other things to see that I get all of Z5. So that Z5 has 4 generators. However, Z6, for example, turns out to only have 2 generators, 1 and 5. Not 2, 3, or 4. Z6 has 2 generators. 2, 3, and 4 do generate cyclic subgroups of Z6, but they don't equal Z6. 2, for example, generates 2. 2 plus 2 is 4. 2 plus 2 plus 2 is 0, mod 6. 2 plus 2 plus 2 plus 2 is back to 2, mod 6. 8 mod 6 is 2. This does not equal Z6. It is a subgroup of Z6, but it doesn't equal it. Cyclic subgroup generated by 3 is just 3 and 0. 3 plus 3 is 0 mod 6, not equal to Z6. Generated by 4 is 4, 2, 0. Same as the cyclic subgroup generated by 2, but not equal to Z6. You're going to get really used to thinking about these kinds of examples a lot. Well, let's end class by looking at something in the book. Let's try to wrestle with a theorem. The theorem is more abstract. Very first theorem in chapter 4. Chapter 4's got a lot of theorems and a lot of corollaries, which are theorems too, but they're called corollaries because they're easy consequences of other theorems. Trivial consequences. Maybe you might even say ways of restating the same theorem. Let G be a group. This is the criterion for A to the I to equal A to the J. Let G be a group and let A belong to G. This is abstract. G is not equal to Z necessarily, or Zn. And in fact, it's not necessarily cyclic. They don't say G is cyclic. If A has infinite order as an element, then A to the I equals A to the J if and only if I equals J. But if A has finite order, say N, as an element, what's the order of an element if it's finite? It's the smallest positive power that brings you back to E, the identity. Then the cyclic subgroup of G generated by A consists of these N elements. And A to the I equals A to the J if and only if N divides I minus J. Now you can think about this with the Zn examples if you like. Though remember, it's not exponentiation in that case, it's adding elements to themselves. Like we just did essentially with a few minutes ago. But I want you to realize you can think about this as an abstract example and even do calculations with abstract examples like this. It's the first bit of advice about wrestling with the theory in this chapter. Suppose G is an element, or A is an element of G with, say, order 6. I'm not saying what the group is. It's just an abstract group. I'm not saying what the element is, though I am saying the element has order 6. So 6 is the smallest positive power of the element that brings you back to E, the identity. G is a group, so it has an identity. The cyclic subgroup generated by A could be written always, well, in this way, first of all. Seemingly, it could be an infinite set because Z is infinite. And N, by the way, it can be a negative number. Oh, let's start with maybe -9, then -8, then -7, then -6, -5. Bear with me. Go ahead and write all this. I think this is worth doing. You could say this is what the cyclic subgroup of A, cyclic subgroup of G generated by A equals, by definition. But when A has finite order, like order 6, this simplifies quite a lot. Seemingly, it's an infinite set, but in reality, it's not. For example, the fact that A has order 6 means this equals E. Of course, by definition, A to the 0 is also equal to E. What about A to the 7th power? By a property of exponents, that's the same as A to the 6th times A to the 1st. But A to the 6th is E. A to the first is A. This equals A. A to the eighth is A to the sixth times A squared. E times A squared. A squared. Likewise, A to the ninth will be A cubed. A to the 10th will be A to the fourth. A to the 11th will be A to the fifth. A to the 12th will be A to the sixth, which will be E again. It's cycling. That's why these are called cyclic. Going with negative powers, you got A inverse, which is A to the negative 1, A to the negative 2, etc. What about like A to the negative 6? By a property of exponents, that equals A to the sixth inverse. E inverse, which is E. So if A to the sixth equals E, then A to the negative 6 will also equal E. What about A to the negative 7? Might be a little trickier here. A to the negative 7 is A to the negative 6 times A to the negative 1. But we saw A to the negative 6 power is E. This is the inverse of A. Something else important here that I haven't mentioned is the inverse of A can be written as a positive power of A. It's A to the fifth. Why? Because A to the sixth equals E, and A to the sixth is A to the fifth times A. Therefore, A inverse equals A to the fifth. Anyway, what all this is illustrating is that you get equality with these things when the order is 6. You can say, for example, A to the 11th equals A to the 5th because 6 divides 11 minus 5. In the theorem, it said n divides I minus j. 6 also divides 5 minus 11. Another thing would be the same here would be A to the 6th, A to the 17th, and A to the 23rd, and A to the 29th. I keep adding 6. Those are all numbers that if you subtract 5, you get a multiple of 6. A to the negative 1, A to the negative 7, A to the negative 13, A to the negative 19. I keep subtracting 6. So you understand theorems, first of all, by examples. Yes, study the proofs too, but examples will definitely help. Think about abstract examples like this too.